Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started. I'm very happy to have Zhenmin Li here. Zhenmin is a PhD candidate working with Professor Yuanyuan Zhou from the University of Illinois at Urbana-Champaign. And his research interests include computer systems, software reliability, data mining, storage systems, and energy management. Zhenmin's recent work demonstrates the success of using data mining techniques to solve real problems in computer systems. So, welcome to Microsoft.
Thank you. Thanks for attending my talk. So in this talk, I will talk about how to use data mining techniques to solve the problems in computer systems. So the modern computer systems desire several properties such as high reliability, high performance, and good manageability. So to deliver such kind of properties requires a lot of effort from the human beings. For example, in order to build a reliable software, it needs spend a lot of effort on debugging and testing. For a complex system, it also needs a lot of experienced administrators to manage the system, install and upgrade the software, backup data, and reconfigure the systems. So such kind of human effort can result in high cost in development and management. In some systems, the management is even more expensive than the equipment. And also, this kind of human work can easily introduce errors into the systems, which in turn can hurt the performance and the reliability of the system. So how can we reduce the cost and the errors in management and development? A desirable way is to automate the procedure of development and management so that we can minimize the intervention of the human beings. For example, we can provide an automatic tool for the programmers so that then they can detect the tools automatically before ship the software. And also in a complex system, we can enable the system to analyze themselves. So in order to do that, we have to enable the system so that they can analyze them by the computers. This is the first step to achieve the automation goal. So my research is focused on this direction. So to analyze the system by computers, we have to analyze the systems. So fortunately, we have a lot of data for the system analysis. For example, we have source code, development document, crash report, network traffic, SQL traces, and so on. And each type of this data is very huge. For example, Linux has hundreds of versions with millions of lines of code in each version. And someone estimated the number of the crash reports in Microsoft. They collect more than 20 million crash reports from each day. That means around 9 billion crash reports per year. So this huge amount of data definitely can provide useful information for us to analyze the computer systems. On the other hand, it is also a challenge for us to address this problem and how we can extract the useful information from such kind of huge amount of data. So in order to address this problem, my approach is to apply data mining techniques. Data mining can automatically extract the hidden predictor information from a huge amount of data. The advantages of data mining are automatic, effective, and also it can apply to a big problem. So data mining is not a magic tool. in order to apply data mining, we still have a lot of challenges. For example, we have such kind of huge amount of data. What kind of information we should extract from this data? If we feed all the data to the mining algorithm, it definitely can cause a lot of noises. And also, we have so many data mining algorithms, which one is suitable for our purpose. And if the off-the-shelf of the algorithms are not suitable for our problem, we also have to design or propose some new algorithms. And after we extract the information from the large data sets, what we can do to exploit such kind of information so that we can improve the systems. So in order to address such kind of challenges, we not only need to understand, have the knowledge about the data mining, also we have to understand the computer systems. So in this talk, I will describe how to apply data mining techniques to solve some problems in computer systems, including the software reliability, system performance, and manageability. So for software reliability, I propose two automatic debugging tools called PR Miner and CP Miner. Both of these tools use data mining techniques to analyze the source code and automatically detect the bugs in the source code. And these tools have already been successfully applied to the real large applications, such as Linux and FreeBSD, and found a lot of new real bugs. And besides of the automatic debugging tools, I am also studying the characteristics of software bugs. This work is based on text mining techniques to analyze the bug reports in a large bug databases. So besides the software reliability, I'm also working on the system mining for performance and manageability. For example, CMiner use data mining techniques to analyze the access traces in a storage system so that it can catch the patterns in access. And using such kind of patterns, we can improve the performance of the storage systems. I also propose a framework called UClog, which uses data mining techniques for intrusion detection. So due to the time limit, during this talk, I will focus on PR Miner and CP Miner and briefly introduce C Miner. Besides of system mining, I was also involved in some other projects, such as energy management for storage and memory, network protocols, and bug benchmarks. So first, I will describe how we can use the mining techniques for software reliability. So why we should focus on software errors? Actually, based on some recent reports, software bugs are very costly. For example, more than 40% of system failures are caused by software bugs. And they cost around $60 billion per year for the United States. And in order to reduce the number of the software bugs, a lot of companies spend more than half of the development cost on debugging and testing. So in order to reduce such kind of cost, we have to improve the software reliability. And to address such kind of problem, first we have to understand what kind of bugs exist in the real applications. So I did a study on the real application. This graph shows the distribution of the bugs with different root causes. I classified the bugs based on the root causes, such as memory-related bugs, concurrency bugs, and semantic bugs. So from this graph, we can see only around 16% of the bugs in Mozilla are caused by memory errors, such as memory leak and buffer overflow. And in contrast, the semantic bugs is the major type of bugs. They account for more than 70%. And these bugs are application specific, and it is hard to be detected by the existing tools, such as Purified and so on. And in order to detect such kind of bugs, we have to provide a lot of information about the applications. For example, the programmer may need to provide the annotation and specification for the applications. So you may think that the semantic bugs are not as severe as the memory-related bugs. However, from my study results, it shows that more than 40% of crashes are caused by semantic bugs instead of memory-related errors. And so in order to improve the availability of the system, we have to address the semantic bugs. Yes?
So what do you include as concurrency bugs? Because I'm surprised at the small fraction. Is it just data races? Do you consider deadlocks or other bugs? And sometimes it's hard to kind of figure out if a crash is caused by a data race, because that could be way past and it corrupts some data structure really early on, and you don't even know about that.
Yeah, good question. Actually, in my study, I used the bug reports that, and this. For this bug report, the bugs have already been fixed by the developers. So from the reports and fix, we can figure out what is the root causes.
Okay, so what's concurrency? Is it just data races?
Concurrency bugs include everything, including deadlock and data races. But this percentage may be not represented for the real application because some data race bugs is hard to reproduce.
Right, it's hard to fix.
Yeah, right.
Say that these are the easiest bugs to fix.
Yes, exactly.
So how do you characterize semantic bugs? So any kind of type safety error, is that considered memory related? Or what is the distinction that you're making between memory
so when we do the classification, we first classify them. If the root causes are caused by memory-related bugs, maybe it also belongs to semantic bugs, but I still classified as a memory-related bugs. So the remaining is only caused by the application specification. For example, when you need to initialize some devices, you forget some steps. This kind of root cause is classified as semantic bugs.
So is it fair to say that basically, if it's not memory related, if it's not concurrency, it is semantic?
No. Also, sometimes it's concurrency, and also some other design problem like that. So now I showed some real example for semantic bugs, so you can see what is semantic bugs. So this example shows the bugs violate some application specification or rules. For example, here this piece of code tries to initialize the SCSI devices in Linux. And in order to correctly initialize the device, we have to follow 3 steps. First, we need to allocate the resource for the device, and then attach this device to a SCSI host. And the last step, we should scan the SCSI host so that we make the SCSI device make the device work. However, in this real piece of code, we find that the program misses the last step, so it causes the real errors in the SCSI device. And there are some other types of semantic bugs. For example, typos or copy-paste related errors, and sometimes the program may miss some exception handling cases. And here I showed an example for the copy-paste related errors. The programmer tries to copy the first loop to the other one. And after copy-pasting, the variable total should be replaced with taken. However, the programmer forgot to replace the last variable so that the replacement is not consistent, and it caused a box here. So both of these two semantic bugs can be detected by PR minor and CP minor, and I will describe how these two tools work in the next slides. So as I just mentioned, the semantic bugs are specific for the different applications. In order to detect them, we have to understand the application-specific information. How can we get such kind of information? A straightforward method is to provide this information by programmers. However, for the large application, it is impractical to get because it is a very tedious work for the programmers. So a desirable way to get this kind of information is to extract this information automatically from the existing source code, and which is what the PR miner does. So PR miner can extract the program rules from the source code automatically, and program rules actually are very common in the applications. For example, when we call spin lock, we have to call spin unlock after a while. And for Postgres, after we call search syscache, we have to call release syscache in order to avoid memory leak. And these rules are application specific, and actually they only exist implicitly in the source code and not documented well by the programmers. And besides the rules with only a pair of function calls, actually there are many more complex program rules in the applications. Here I show an example that involves that the rule involves 4 different function calls and some related variables. So these rules appears many times in Postgres, and the programmer should follow such kind of rules. So how can we extract such kind of complex program rules? Actually, this is PR miner does. PR miner can automatically extract all these the program rules from the source code, and we don't need to provide any rule templates. And we can extract the rules with different types of elements. For example, the function calls, variables, and data types. And also, the rules can involve any number of the elements. So after we get such kind of program rules, we can use them to check against the source code. And if we find any violations, they can indicate some potential errors. So the next question is, how can we extract such kind of program rules? The idea of PR miner is based on the observation that if the elements are frequently used together, then they can indicate some kind of association between them, and it can infer some program rules. For example, in Linux, spin lock and spin unlock appear for more than 3,000 times in Linux. And if we can find all these associated elements that are frequently used together in the source code, we can infer the programming rules. So how can we find such kind of frequent used elements? Actually, the frequent item set mining is one suitable method to find all these associations. So what is frequent item set mining? So frequent item set mining is frequent item mining tries to find all the frequent subsets in the item set database. An item set is a set of number, and a large number of the item sets can compose of an item set database. For example, in this database, we have 4 different item sets, and we call the number of the appearances of sub-item sets as support. Here, the sub-item set ABD, the support is 3. So the frequent item set mining finds can find all the frequent sub-item sets from a large item set database. For example, if we consider the support with 3 as frequent, then the mining algorithm can find A, B, D, and A are frequent. So the idea of frequent item set mining is based on the observation that if an item set is frequent, then all of its sub-item sets are also frequent. Based on this observation, we can construct the longer frequent item sets by combining the short frequent item sets recursively, so that we can find all the frequent item sets in a database.
What is the complexity of this algorithm?
So the worst case is exponential, but for the practical problem, actually it is quite efficient because it does a lot of optimization. So after we find the association, find all the frequent item sets, we can generate the association rules based on them. For example, we can generate the rules AB to D, which means if AB appear, then D probably also appear together. And the probability is 100%.
What is the difference between saying that ABD has a high support as opposed to saying that AB implies D?
Sorry, what is the question?
So what is the difference between the following 2 facts? So the first fact is that AB and D, this set has a high support, as opposed to saying that A and B implies occurrence of D.
A, B applies B.
Yeah, how is the conditional different from the joint? In other words, why is having A, B, D be
actually, we have a lot of rules. This is only 2. We can also invert AD to B or BD to B or B to D. There are a lot of rules.
Is there any extra information you get to get the conditionals from the joint?
We can generate all kinds of possible rules. Actually, we don't consider which one is conditional, which one is the result.
So it's equivalent?
Yeah, equivalent.
Okay.
But if they are on this, for example, A to B is 75%, but B to A, it is 100%. The probability is different. Right? So, now, so in order to apply the data mining the frequent item set mining to find the program rules, we have to address a lot of challenges. For example, the mining algorithm can only work on the numbers. So we have to tokenize the source code into an item set database. In this pre-processing step, we have to consider a lot of issues. For example, what kind of information in the source code should be tokenized? If we tokenize all the source code, we may get too much noises. Also, after we get the frequent item set, we also need to convert the frequent sub-item set into the program rules. And we also have some kind of some other issues, for example, exponential problems. And I will address these issues later. And after we get this kind of program rules, we can use them to check the source code. And any violation to this program rules can indicate some potential errors. So now I will discuss a little bit more details about how to tokenize the source code. So the first step is we need to build an item set database. So what information in the source code should be tokenized into a number? Because we want to find the association between among the elements such as function calls, variables, and data types. So we tokenize this information into numbers. And what should be converted into an item set? There are a lot of choices. For example, we can convert a basic block into an item set. However, basic block is too small because some program rules, it some program rules may be across different basic blocks, and using this unit to tokenize as an item set, we may lose a lot of program rules. So how about file? Actually, it is too large because in some cases, a single file may contain the same program rules for many, many times, and so we may also lose such kinds of program rules. A suitable unit for an item set is a function definition, and PMiner use this as a solution. And after we convert each function definition in the application into an item set, we can build an item set database. And here, I showed an example for passing the source code. So first step, we need to decide what kind of information should be tokenized. So there are a lot of issues. For example, for local variables, for the same program rules, the local variables may appear as different identifiers in different function definition. So if we tokenize the variable names into a number, we may also lose such kind of rules. So in order to address this problem, we can use the corresponding data type for the local variable, so that even in different definition, the data types are still the same. And there are a lot of other issues when we pass the source code. And if you are interested in the details, we may discuss it offline. So after we pass the function definition, we can build an item set, and the whole program can be converted into an item set database. Now, we can apply the frequent item set mining algorithm on the item set database. And after that, we can get all the frequent sub-item sets. And each frequent item set corresponds to an programming patterns. For example, here, this programming patterns corresponds to this frequent item set corresponds to program patterns that involve 4 different function calls. So from this programming patterns, we can generate the program rules. For example, here, from the program pattern we just found, we can generate 14 different program rules. And actually, in some large applications, we can find some programming patterns that involve a lot of elements. For example, in Linux, we find a lot programmers involve more than 20 elements. And if we generate all the program rules, then we may have some exponential problems here, and it is impractical to generate all of them. In order to address this problem, we can use the closed rule mining algorithm, so that we can reduce the redundancies of the subrules and rules. For example, here, the scarcity host to host allocate actually involved in scarcity host to add host actually involved in these rules. So use the closed mining algorithm, we can reduce such kind of redundancy. In order to do that, I propose a new algorithm here, and due to a time limit, I may skip the detail in this talk. Now we have already obtained the program rules from the source code. Now we can use this kind of rules to detect the violations, which indicates the potential errors. However, if the probability for program rules is too low, that means this rule is not trustable, so that we can ignore them. And for the rules with probability of 100%, which means all the elements are always appear together in the source code, which means there is no violation in the source code. So this means that if the probability of a rule between the threshold and 100%, then there are some variation here. For example, we have two program patterns, and we can generate a rule with a probability of 93%. And this probability indicates there are some violations of this rule. And actually, there are two cases that misses the function called scan host, which is the real bugs in the Linux. Yes?
So this seems very similar to Dawson Angler's belief system kind of work. Can you comment on that? And have you compared head-to-head against their system?
Yeah, sure. Good question. So actually, my work was inspired by Dawson Angler's. And however, in Dawson Angler's work, they need some prior knowledge about the applications. First, they need to provide some fixed rule templates by the programmers. For example, the templates like function A must be paired with function B. And actually, in my experiments, we found a lot of rules that contains more than 2 function calls and some related variables. It's very hard for the programmer to provide all these possible rule templates. And also, in Dawson Angler's work, they also need to use some prior knowledge about the function naming convention. For example, they give more weight on the lock and unlock so that they can rank the rules. And in my method, I don't need such kind of prior knowledge, which means this one can be more automatic.
But
Yes.
Can you compare on the same benchmark, like which they use, because they found some bugs in Linux kernels. But I'm just wondering if you could find the bugs they found with kind of less programmer help, or you could even find more bugs.
I did on different programs, and all this. So I'm not sure the bugs can be detected by both of these tools, but I think if the errors violates some complex rules, then Dawson Angler's cannot address this kind of errors. So because of this kind of difference, I think my tools can detect some more bugs with that violates the complex rules. I didn't compare based on the same benchmark. Yes?
So one advantage which I feel you did with Dawson and your style of work, in which you let the programmers specify these patterns and then you check for violation of these patterns, is that you won't get any false positives. So I think our question boils down to the fact, is there more effort involved in writing down these specifications, or is there more effort involved in filtering out the false positives by hand?
Yes, that's true. Actually, in order to automate the procedure to extract the rules, we have to tolerate more false positive rate. But that is a challenge in this work. We have to deal with a false positive rate.
So, in the case where you had, say, scan host in a procedure that gets called from the procedure that has the other 3, you're not going to detect that through these item sets, right? Because you won't, you're only looking at items within the function. But do you do some kind of analysis to eliminate that as a false positive then in the subsequent program? Because clearly there's a single control flow path that will get to scan host after it goes to these other things, and you could conclude that's not a violation, right?
Yes. So
did you do that, or does that present itself as a problem in terms of the analysis?
Actually, right now I only did some inter-procedural analysis to reduce the false positives. And for example, some rules may across different functions. And I still analyze the caller or callee's paths so that I can prune some false positives. And up to now, I only work on that. But in the future, I would also like to adjust. For example, I can also consider the path, different paths or branches, so that it can also reduce the false positive. So as I just mentioned, I used some interprocedural method to reduce the false positive rate. And after pruning, I ranked the error report by the probability and the suppose. So based on this ranked reports, the programmer can decide how many reports they can verify. So this this table shows the program rules extracted by PR miner, and for the column function, this means this rules only contains the function calls, and for function variable means the rules contains both our function calls and variables or data types. So from this data, we can see that PR miner can find a lot of rules, and among these rules, most of them contains both our function and variables, which means it is quite important for us to consider the information about the function calls and variables when we extract the program rules.
I'm confused because in the item set slide,
Yes.
you said, at least I took it, that you kind of ignored variables because you didn't know there could be aliasing when you call parameters in and they're called things.
Yes, exactly. So actually, I set local variables. Actually, there are a lot of global variables which I still use the name for the global variables. And here, variable also stands for data types and variables.
And instance variables in classes too? Or is this not C++? It's just
it is just C.
Oh.
Right.
So most of them are function variable PR rules.
Right.
Are those useful in the real bugs that you discover?
Yes.
You get more, but are they useful?
Yes. When I verified by manually, I found actually it is quite useful when we consider these rules involve variable. For example, when we allocate some memory for some different object, for example, different devices, the data type is different, and different data type indicate different object, and it should follow different procedure. Although it's also called the malloc at the first step. Does it make sense? Okay. So PR miner can detect hundreds of the potential errors in Linux, and I manually verified the top 60 reports. And within these 60, 16 of these bugs have already been confirmed by the developers.
How do you rank them when you say the top 60?
The top 60, I use the probability and the support. So since PR miner uses data mining techniques to extract the rules, it is quite efficient. For example, for Linux, in order to extract the rules from millions lines of code, it only takes less than 1 minute to less than 1 minute. Okay. Any question about this part? Yes.
Can you go back to slide 27 real quick? 27. Yeah. Here, are these 16 bugs the top ranked bugs out of the 60 that you considered?
It is the distribution like a little bit like that. It is dropped, of course.
Oh, so
Yes.
if you rank all these bugs and start going to number one, there's a very good chance that
Right.
that is a bug.
Right.
And then as you go down the list, at some point you'll find too many false positives and
Yeah, then
and
you can
quit.
stop. Yeah.
Okay. You don't have to dig through.
Right. Exactly. So now I will briefly describe how CP miner detect copy-paste code. So copy pasting is very common in development. And from some previous studies shows that more than 12% of the code in the file system in Linux are from copy pasting. And copy pasted code can easily introduce errors. I have already shown an example in the first slides. So in order to detect the copy-paste errors, first we have to identify the copy-pasted code in an application. So how can we detect the copy-pasted code? It's based on the characteristics of copy-pasted code. First, the copy-pasting is based on code, and also it appears for at least twice in the whole application. And there's another challenge here, because after copy-pasting, the programmer usually needs to change something in the pasted piece of code. So these two pieces of code may not be exactly the same. CP/miner use data mining algorithms to find the copy-pasted code. And here I use the frequent sequence mining, which is a little bit different from the algorithm in PR/miner. Frequent sequence mining can also consider the order of the items. The reason is that when the programmer copy and paste a piece of code, usually they don't want to change the order of the statements. So there are some other differences between the PR/miner and CP/miner. For example, in PR/miner, we also consider the typed information, but in CP/miner, we only consider the lexical information because it is copy-pasting is based on code. And also, CP/miner use the statement as a unit to tokenize as an item. The reason is that for programmer, they usually copy the whole statement instead of part of the statement. So use the statement as a unit, it can be more efficient. And here, this table shows the results of the CP/miner. From this table, we can see that PR/miner can detect a lot of copy-pasted code in large applications such as Linux. It contains more than 20% of copy-pasted code. And CP/miner can also detect a lot of copy-pasted errors in the latest version of Linux. For example, in Linux, it detects around 50 bugs, and for FreeBSD, it detects around 30 bugs.
So all those bugs, the same types of bugs, where the replacement is not complete.
Yes, not consistent.
Not consistent.
Yes, right.
So is there, were there false positives?
Yes,
Okay.
right.
So, okay.
Actually, the current version of CP/miner, the false positive rate is quite high. So the reason is caused by the switch cases statement, because for some large switch cases statements, it's hard to match which part is copy paste from each other. So this can cause false positives, and actually, this causes more than 70% of the false positives. So if we can exclude this kind of consider this situation, especially we can increase the accuracy of CP/miner. Any other questions? So now I go to the other part of my talk, is how to use data mining techniques for storage systems. So storage systems is very complex and intelligent now. For example, some storage system contains more than 80 CPUs and more than 64 gig memories. So if we can exploit such kind of intelligence in a storage system, we can definitely improve the storage systems themselves. However, when we exploit such kind of intelligence, we have a lot of challenges. The main one is the interface between the storage systems and the storage client. The interface is very narrow, which only based on operations of block, for example, read and write blocks. And so the clients cannot notify the information about the application to the storage systems. So actually, there are some previous work also working on the patterns in the storage systems. However, they only adjust the simple patterns, such as locality and spatial locality and temporal locality in the access patterns. And C minor can find much more complex patterns in the access in storage systems. For example, the block correlations. Here I show an example for the file systems. In this, if the client is file systems, actually there is some correlation between the directory and the subdirectory. Also, there is some correlation between the inode block and the data block. So all these correlations are actually semantically linked together, and using some simple method, it's very hard to identify such kind of complex patterns. If we can find such kind of correlation between the blocks, and we can use them to improve the systems. For example, if we find a block is red, then we can prefetch the correlated block in advance. Also, we can do disk layout or caching management or energy management so that we can exploit such kind of information about the block correlation. So in order to extract such kind of block correlation from the storage system, there are a lot of ways. It can be classified into 3 classes: white box, gray box, and black box. So white box need to modify the interface between the storage system and the applications, and also it need to modify the client side, and which is not practical for the real products. So a gray box doesn't need to modify the interface. However, it also needs to make some assumption about the client. For example, the semantically smart disk system proposed by Wisconsin is a gray box method. They need to assume the client side is a fast file system format. So my method C minor is a black box, which does not need to modify any interface between the storage system and the clients, and also it doesn't need to make any assumption about the clients. So how can we use the black box method to obtain the block correlations? The idea of the C minor to get the block correlation is based on the observation that if the blocks are frequently accessed together closely, then they indicate the correlation between these blocks. So similar to PR minor or CP minor, we can apply the frequent pattern mining algorithm on the access traces so that we can figure out what blocks are accessed frequently together.
Question?
Yes?
So is your frequent sequence mining algorithm also exponential?
Yes, exactly. So this graph shows the block correlation in the real system in the file system, Trello file system. So this graph shows the correlation between 2 blocks. And if we have a correlation between block X and Y, then we plot a point in this graph. So each point represents the correlation between the block X and Y. So from this graph, we can see a lot of points on the diagonal, which indicates the temporal locality. And the points around the diagonal indicates the spatial locality. And besides these simple patterns, C-miner can identify many more complex correlations, which means C-miner is more powerful than the previous work. So after we extract this block correlation from the star system, we can use them for prefetching to improve the performance of systems. This graph shows the bit ratio improvement and the response time improvement when we exploit the block correlation for prefetching, and the results shows that by exploiting the block correlation, we can improve the performance more than 20%.
Is this a simulation?
Yeah, this is based on the BigSim simulator. And however, this workload is a real workload.
So I have a question. I don't exactly understand. So if your analysis is exponential, you can't do this in an online fashion, right?
No, this currently I use the offline algorithm to analyze the access traces, and I also analyze the stable pattern. I mean, how long the pattern can be effective. For example, in Trello Lite 2, I mined the patterns from 3 hours traces. It can be used for 1 day, and the improvement still keep at around 20%. That means we don't need to analyze the trace very frequently.
These patterns are workload specific, or you can mine some rules and apply it generically to other environment. Because you're talking about runtime.
Yes. Actually, this is the patterns are application specific.
Yeah, but how general you can apply this to?
So for the real applications, actually for data center, the application are very actually the client application are also very stable. They usually, for example, the client are always database, are always file systems. They won't change the file system into database. So these patterns are.
You mine the patterns from this data center, and later you can.
You cannot apply this on another applications.
But to another data center?
No, you cannot. So to conclude my talk, my work demonstrates that data mining techniques are very effective and practical and promising to solve some problems in the computer systems. And in the future, I would like to continue my research direction. First, for example, I can extend the current research in the static analysis. For example, I can also combine some information about the context and the path so that I can increase the accuracy rate in the PR miner. And also, I can apply the similar techniques on the software evolution so that we can find some how the program rules change between different versions. And also, the similar idea can be applied on the dynamic analysis. We can use the mining algorithm to analyze the execution traces so that we can get the patterns in execution. And also, we can detect the runtime errors. As a long-term plan, I would like to build an autonomic computing systems. In this kind of system, the computer can look after by themselves. In order to do that, the system have to be able to analyze and characterize by themselves. For example, we can collect the data about the system, and then using mining algorithm or machine learning algorithms, we can extract some useful knowledge from this data so that we can build a knowledge database. And use this kind of knowledge, we can we can implement the self-healing and self-management. And also, we can integrate the runtime error detection mechanism into such kind of autonomic system so that we can build a reliable system. Okay, thanks.
So given the high false positive rates, do you really think this is realistic? I mean, you're going to fix things and you're not even sure if it's a real error?
So the false positive rate, I think one major reason is caused by the static analysis. We have not enough information to analyze the real cases. But if we can get some runtime information, for example, the execution traces, we can still improve the accuracy. So I think this is still possible. And also, for the false positive cases, actually they caused by some major reasons, and we can consider these major reasons especially so that we can also decrease the false positive rate. Any other questions? Okay, thank you very much.